Okay, so we need to answer your activity, right? Did you do the activity?
Yeah.
Oh yeah. Okay. So let's make your activity. Okay, no, 4. What activity?
4.1.
4.1.
Number 1.
So we're looking at activity 4.1. Please listen to me. Yeah. Okay. So let's look at number 1. So what do they tell you? They tell you that you have a beam that's 8 meters long. This is a beam. This beam is 8 meters long. Has a weight of 750 kgs. So its weight is 750 kgs. Before we do anything else, let's work out that, right? So this would be at the center. This would be mg equal to 750 times 9.81, which is
7357.5.
7357.5 newtons. And the distance from here to here will be what? 4. Right? Because the gravity will act on the center of the beam.
You want to sign that? You want to sign?
Yeah, we're all signed.
Okay, so you sign for the whole month.
Yeah. Okay. Force of 600 newtons acts vertically on the beam 2 meters from A. So this is 600 newtons, 2 meters from A. The force of 1300 acts vertically at 0.6 meters from A. So this here is 1300. So what will this distance be? 4, right? Because it acts 6 meters from A. You already wrote 2 here, so this would be 4 meters. And calculate your reactions at A and B. So it has reactions at either end, force at either end. Okay, what's this remaining distance here?
4.
Now 2. 2 meters.
2.
How do you not know how to do this? When I did it with you on Saturday.
I'm just want to confuse. I just want to confuse everyone.
What you drinking?
Confusing everyone.
Today is not the day to confuse because I confused them later, right? Okay, so this remaining distance will be 2. Sorry guys, this diagram not drawn to scale, right? Okay, this is everything. We have all our information. They want you to work out RA and RB. How would we start this question? You'll take the moments about A, okay? So you'll take moments about A. So after that,
Now you don't look at all forces anti-clockwise.
what? Yeah, so what you need to say first after you write this? Clockwise moments
Anti-clockwise.
is equal to anti-clockwise moments. So now we're looking at A and we're looking at clockwise moments. So if you're looking at A, what would cause the other end to move in a clockwise motion? Would it be an upwards force or a downwards force? Downwards forces, right? Good. So you'll start with 600, and how far is 600 from A? 2 plus 1300. How far is that from A?
6.
Plus your gravitational force, which is 7357.5. And how far is that from A? 4. So now if downwards cause a clockwise motion, upwards would have to cause a anti-clockwise motion. Your upwards force here, RA, remember it acts at A, so you don't have to write that down. How far is RB from A? 8 meters, right? Because it's on the other end. So if you put the whole thing in your calculator, what you get? What you get? 38430. No comma, anything?
No.
Okay, equal to 8RB, and then therefore RB is equal to
480.75.
4803.75 newtons. So that's your reaction force at B. So what we need to do next now, we need to take the moments about B. Okay? So you say take the moments about B. Okay? So you write the same thing again. Clockwise moments is equal to anti-clockwise moments. Okay? Now we're looking at the moments about B. So what will cause the other end to move in a clockwise motion is either your upwards force or your downwards force. Upwards force. You don't understand it so far, guys?
Yeah.
And then you okay? You sure? What you confused about? Because if you don't understand this part, the next thing I'm going to teach you is going to become difficult. Which you confused about, Jay?
Okay, the whole thing, because on the video, I didn't have time to attend to it, because
So you never learned anything about statics at all?
at all.
Yeah, you're gonna have to watch the video, right? Because if I go back to the start, it's a whole lesson there. But what we do that, and then Saturday when I see you,
Okay.
we'll go through everything, right? But make sure you watch the video, right?
That's if she makes it on Saturday.
She'll make it. She'll come. She's not painting tomorrow. It's fine. She's okay. That's why you status. It's fine. Right. So upwards causing clockwise motion. So now RA is how far from A?
Sorry.
RA is how far from B? 8 meters, right? So this should be 8 RA, and because RB acts at B, it's going to be 0, so you're not going to have to write anything down there, right? So if upwards motion caused clockwise, downward cause anti-clockwise. So your downwards forces now we look at. So your first one is 600 newtons. How far is that from B?
606.
6. There's B.
Oh, sorry.
600 is that, right? So this would be 6 meters plus 1300. How far is that from B? That's 2 meters. And your gravitational force is how far?
4
So 8 RA is equal to
35630.
35630.
630.
So therefore RA is equal to
4453.75.
4453.75 newtons. So now how do we check if our answer is right? We'll do a test, right? So when you do the test, you're going to say upwards force. I'm just going to write upwards force is equal to downward force. So all your upwards forces is RA and RP, which is 4453.75 plus 4803.75 must equal to 600 plus 1300 plus 7357.5. So this end equals to what?
92575.
And this end? So your left hand side is equal to your right hand side, therefore the answers you have is correct. Is everybody okay with that?
Is it possible that you can have the wrong answer right? Like if you made it wrong, but you
The last one, right?
Yeah.
You can, but the obviously your method is wrong. Okay.
No, but your forces basically like going down is constant, right?
No, but sometimes see if you have a uniformly distributed load, right?
Yeah.
What can happen is the way you work out that answer,
Yes.
you could have taken maybe a shorter distance and a higher force, or a higher shorter force and a longer distance, and you still come out to the same number, but
Yeah,
what you
that's
chose was wrong.
Then you really special.
Yeah, and then you'll see how that will mess up everything else after, right?
Yeah.
Okay guys, so yeah, take a picture of this. I've got a very important thing to do today, so that's my main aim for today, right?
Yeah. The next one is ish.
Next one is okay too.
No, the next one
Okay, but guys, you okay with this?
Yeah.
Okay.
Next one has a tricky.
yeah.
Okay, let's do 4 points. Number 2. Okay. Number 2, they tell you that a beam with a mass of 100 kgs carries a uniformly distributed load of 130 newtons per meter over its left half. Okay, towards the end they tell you the beam is 7 meters, right? Okay, so your beam is 7 meters. So gravitational force will be mass times gravity, which is equal to 100 kgs times 9.81, which is 981 newtons. Right, let's start again, right? This distance here would be what?
3.5.
3.5 meters. This distance here would be 3.5 meters. This is side A, this is side B. So, a beam with a mass of 100 kgs carries a uniformly distributed load of 130 newtons over its left half. Okay? So, this uniformly distributed load is somewhere here. Okay, now remember we said with uniformly distributed loads, we convert it into a concentrated load. And how would you convert that force into a concentrated load? You multiply by the distance of the load, right? So they told you that it has 130 newton per meter. That will be multiplied by 3.5, which is 455 newtons. But where will that force act? On the center of the distributed load. So how far will that be from A? 1.75 meters, and then here will also be 1.75 meters. So far we understand what's going on, right? Okay. It is supported 1 meter from the left. So this is 1 meter, RA, and it is supported 1 meter from the right hand. So this here is 1 meter, that's RB. Calculate the magnitude of the reaction forces. Right? Exactly like how we would do any other question. What we would start to do? So you'll say take moments about what? A. Right? And after that you would say clockwise moments is equal to anti-clockwise moments, right? So, if we are looking at A, picture A is in the center of your clock, and what will cause the other end to move in a clockwise motion? Would it be upwards forces or downwards forces? Downwards forces. So, your first downwards force is that uniform distributed load. Okay? So, this will be 4, 5, 5, and how far away is that from A? 1.75 plus the other force that acts on it is the gravitational force. So that will be 981, and how far away is that from A? 3.5 meters, equal to. Now if downwards forces causes a clockwise motion, upwards force will cause a anti-clockwise motion. So for here, how far is RA from A? 1 meter, right? Plus, how far away is RB from A? 6, right? So, what does this become?
4,229.75.
4,229.75.
Yeah.
Okay, equal to RA plus 6 RB. Can we do anything further than this?
Yeah.
What?
Add the RB. And you left it for RB.
You're going to be left with, remember, if you're dividing this by 6, you have to divide this by 6. And you have to, the only thing we can do is take one of the terms and make it subject of the formula. What should be the easiest term to make subject of the formula? RA, right? It will be easier because if you make RB, you're going to have to take this across and divide the whole thing by 6. Later on, when you're doing a simultaneous part, it's going to become difficult, right? So nice to have a good linear equation and then that. So you can just say that therefore 4229.75 minus 6RB is equal to RA. We'll come back to this just now. Okay? Let's take the moments about B. So So taking the moments about B, we're going to say clockwise moments is equal to anti-clockwise moments. Okay, so if you're looking at B, what will cause the other end of the beam to move in a clockwise direction? The upward force. The upwards force. Right? So you'll say RA, and how far away is RA from B?
6 meters.
6 meters, right? I know that. Full length of the beam is 7. This is 1 meter.
That's that I'm confused about. See, on the lines, RA not B is 1 meter away
1 meter from here,
from A.
1 meter from here. RB is 1 meter away from B. But from here to here, how far away is RB?
6.
It'll be 6. Because the full length of the beam is 7. It's 1 meter from the right, so this left hand portion will be 6. Okay. So this here would be 6 plus RB times 1, because it's 1 meter away from B. Okay. This is equal to, now if up caused a clockwise motion, down would cause a anti-clockwise motion. So how far away is that uniformly distributed load force from B?
1.5 is 1.75 plus 3.5 is
Right.
4.25.
4.25.
5.
5.25 plus the gravitational force, which is 981, times the distance, which is 3.5. So this becomes 6RA plus RB equal to, and what's that?
5822.25.
5822.25. Can we do anything further? Let's just make RB the subject of the formula. So we'll say therefore RB is equal to 5822.25 minus 6RA. So far guys, everything I did over here, do we understand? Okay, so now we got two equations, right? But there's two different variables that's the subject of the formula. So we can take this and substitute it into there. Understand that? Okay, so you'll say therefore RB is equal to 5822.25. I'm just going to call this equation 2. I'm going to call this equation 1. So you'll say substitute equation 1 into 2. So later on, if I go back and read it, I'll remember what I'm saying. Okay? So 5822.25 minus 6 times. So it'll be 6 into whatever RA is. We said that RA is equal to this. So this will be 4229.75 minus 6RB. Now we have one linear equation with one unknown variable. Yes? So we can solve for that. So this here would be RB is equal to 5822.25 minus 6 times 4229.75.
25378.5.
25378.5, and then minus 6 and plus minus 6 and minus 6 will become
Plus 6.
plus 36 RB. So now we move like terms to one side, and then obviously like that, right? So this would come across and it will become minus 35 RB, because when this goes across it will be minus 36 RB plus 1 RB, which will be minus 35 RB. And when you take this 5822.25 minus this number here, what you get?
Minus 19556.
Minus 19556.
25.
Okay, then you just divide. So you say therefore RB is equal to, and then this number here divided by minus 35.
558.75.
558.75 newtons. Now this is the value of the reaction force B. We still need to get A, and how we get A, we use this equation here. So you say therefore RA is equal to 4229.75 minus 6 times 558.75, and that's equal to
352 is 877.25.
877.25 newtons. So now we worked out a value for RA, we worked out a value for RB. How will we know the values are correct? You'll test. So you'll say test, which is upwards forces must equal to downwards forces. So we have two forces acting up, which is RA and RB. This is 877.25 plus 558.75 equal to your downwards forces. We have two forces there. 455 plus 981. What is this side? What is this side?
1436.
1436. This side is also 1436. So your left hand side is equal to your right hand side. So you know that these two values here are correct.
Okay, I'm special.
What you
So after I tried to do one, I ended up with a 1 and a 6 and I don't know what to do. And then I read the question, so I understood the question to say when it says calculate the magnitude of the reaction forces. So I used RA and RB. So I took the moments of RA and RB. So I don't
about
about
RA
RA and then I took a moment about RB, so I don't end up with two.
simultaneous equations.
It confused me, but I considered it also. So with all the forces, I worked out from RA, which was the 1 meter in.
So you took it like as a point here and
Yes,
here.
yes, not A and B's
But
point.
then how you did this portion here? Because remember, this uniformly distributed load will also be
So
applied
I
to force.
ended up changing all. So like my gravitational force would be 2.5, and then
Yeah, no, I understand this side part, right? Because this here would cause you to move in a clockwise.
0.75 on the 455 newtons. Yeah, change gave me a lot of.
But you still get the
confusion.
same
I
answer.
got the same answer.
I'm trying to figure out how, because see, okay, this part here is fine. Down would have caused you to move in a clockwise, right?
Yes.
And then and then the up would have caused you to move in a anti-clockwise.
Yes.
But you see, with this uniformly distributed load, you have this portion here,
Yeah.
right?
Yes.
Which will also cause a downwards force, but on the left of that reaction force. So when it's going downwards here, and if it's pushing down, it's going to create an anti-clockwise motion on this end. So then you figure out what I'm saying. But try to
But
stick,
anyway, I'm going to stick with you.
To this
because I
method,
was
right?
confused. I tried
Yeah.
to.
because you never know whether that
School.
same thing you did will work on another question.
Yes.
Okay? So, how are we doing at 10 there?
10 to 1.
10 to 1.
Mm.
Shit.
No, we got chemistry, so it's on there.
So, this is this. Are we okay with this?
Yeah,
Yeah, now I understand.
Are we okay? Are you?
it makes sense.
Now I feel stupid that I
The
didn't
problem is, when you go to the first equation, you don't know where to go.
See, then
Yeah.
when things like that happen in the paper, right, it's gonna happen, right? Because you never saw the question and stuff before. Carry on working like how you would normally work out the question. Because if you came over here and you got stuck, okay, I got two equations, and you know why you got two unknown variables here, because the supports are not in the ends. So one of them never cancelled off. Right? So you're gonna end up with this. Carry on working the question like how you normally would. You would have ended up with another equation. Remember, when you're given an equation that has two unknowns, to solve for the two unknowns, you need to have two equations. And that's how you do simultaneous equations. So you need to work and find a way to see how you can get one more equation that includes one of the unknowns you have. And then you can substitute it into it. Okay. And take a picture or take it down and do it. Okay. Now we're doing something today which is called shearing force and bending moments. Remember last week Temba was fighting with me and he said, hey, this cantilever, what happens if it's on this end? It's gonna bend, it's gonna break, this it's closer if it's there, blah blah. This is how we're gonna do it. Right?
Temper is always problematic.
Temper, I'm telling you, in the union right? So, I'm looking at page 72. Okay, guys, please pay attention to this thing here, because if you can get that first example and understand what I'm saying, everything else will come easier. Okay? So, shearing forces and bending moments, shearing force, bending moments, and applied forces are closely related to each other. So, consider the cantilever AB in figure 4.10, which is the figure above. For equilibrium, the vertical reaction force A must be equal to the load W. You all understand what they say about that? So remember, with the cantilever, you only have a support on one end. That support would be at A. So A needs to be pushing up enough force so that when the load of W comes down, this is in equilibrium. Because what will happen if W is greater than the support? It's gonna break, right? The cantilever must therefore transfer the effect of load W to the support at A by developing a resistance to the load effect. This is called your shearing force. The beam must also remain nearly straight. Don't highlight that for shearing force, I'll give you the definition for it, right? The beam must also remain nearly straight, so it must also develop a resistance to bending, which is what Temba was asking last week, right? Because remember, as Temba said last week, if you put that weight closer to the support, it's not going to bend as much as if you put it on the edge. Okay? So, failure to transmit the shearing force at any given section, so that, you see where they got the X and the dotted line? They're basically referring to the shearing force is taking place there. It's going to basically break or fracture at that point. Okay? We understand so far we're looking at? Okay? Failure to sufficiently resist the bending effect of the load will cause the beam to deform as shown in the figure 4.12. So, I'm going to say it again. Failure to transmit the shearing force at the given section will cause the beam to fracture. So, your shearing force will basically determine whether the beam will break or not. Okay? Your bending effect will obviously determine whether the beam will bend. Understand what I'm saying? Okay, so failure to transmit the shearing force will cause the beam to break. So breakages will occur because the shearing force is greater than whatever force is being supported. Right? And the failure to sufficiently resist the bending effect will cause the beam to bend. Okay, so obviously bending forces will be applicable to bending, the beam bending, and shearing force will be applicable to the beam breaking. Okay. The shearing force transmitted across the section Y to Y may be considered as the force that is necessary to maintain the equilibrium if the beam is cut at Y to Y. Your shearing force is called Q, and between the shearing force Q between A and C is equal to W. So you see from where A is in the diagram below. Okay, so, yeah. So where A to C is, the W that's being applied. That force of between A and C needs to be equal to W for this beam to be in equilibrium. Notice that the shearing force between C and B is 0. So everything after that point is going to be 0 because why? There's no support that's acting on it. Okay. The bending moment MS between A and C is equal to the weight that's being applied multiplied by its distance. See figure 4.13. So all this, relax. I'm going to explain everything to you with a good example. Okay. Sign convention is, you all know, understand what sign convention is, right? When we take either something as positive, up as positive, down as negative, that's sign convention. Okay. So sign convention. Shearing forces and bending moments are both vector quantities, and a convention of signs is used to distinguish between the values of opposite meaning. When drawing a shearing force or a bending moment diagram, the following sign convention must always be used. So, for you to take something as positive, I'm going to try, let me take this off, right? Okay, so in terms of your sign convention, if your beam looks something like this, okay, and then it was fraction, so obviously the other piece would be somewhere here. If the weight is being applied, so this is where your shearing force would occur. This would be left of your shearing force, this would be right of your shearing force. Okay? Okay. Now if a weight force was being applied there, you would take it as a positive on the left hand side of this. Okay, so the only time you would take positives is if your weight on your left hand side of your shearing force acts upwards. Okay? On the right hand side of the shearing force, if your weight is pushing down, you would take that as positive. Understand what I'm saying? Okay, so where your shearing force is, on the left hand side, forces acting up, you would take as, or your weight force acting up, you would take as positive. On the right hand side of your shearing force diagram, if your weight is acting down, you would take that as positive. Okay. For negative, you would say, if this is your diagram, and if this is where your shearing force acted, if whatever force is acting down, you would take that as negative on the left hand side of your shearing force, and then whichever force is acting up on the right hand side, you would take that as negative. Do you guys understand what I'm saying? So if you look at it there in the diagram, wherever your shearing force is, you're going to get a left and right. Okay, the left of your shearing force, the right of your shearing force. Okay, whichever force is pushing upwards on the left hand side, you take that as positive. Whichever force is pushing down on the left hand side, you take that as negative. On the right hand side, whichever force is acting down, you take as positive. Whichever force is acting up, you take as negative. Do you understand it? Okay. So next page they tell you, and then for your bending moments you'll see how it will bend. Okay. Definition of a shearing force. A shearing force at any section of a beam is the algebraic sum of all the forces to the left or the right section. Definition of a bending moment. A bending moment of any section of a beam is the algebraic sum of the moments about the section of all forces to the left and right of that section. Its definition, you must know it, okay? So they tell you consider the beam in figure 4.15.
Okay, so definitions we're going to do.
Yeah, that's the definition. Okay, while you are making a note of it, let me draw this. Okay, so this is the diagram that they gave you, and I'm going to use this diagram to explain exactly what I meant over here. Okay, so this is your scenario. You have a beam, okay, supports on either end. You have one concentrated load here, W1, which is a distance A1 from the shearing force. Okay. So remember, this X dotted line is your shearing force, that's where the beam fraction. Okay, so you have W1, which is a distance of A1 from your shearing force. Okay? You have another concentrated load of W2, which is a distance of A2 from your shearing force. Okay? You have another one of W3, which is a distance of A3 from your shearing force. The distance of your RA is A distance away from X, and your distance of your RB is B distance away from your X. These are just variable names. Okay, so in the beam, the shearing force and bending moment of section X, well, XX being a shearing force, or where the fracture occurred, can be calculated as follows. So, to the left, of XX, right? Your shearing force which is called QS would be equal to what? Now let's look at our sign conventions, right? So this is where the fracture occurred, this is where the fracture occurred. Which forces would you take as positive? Your upwards forces, right? So in this instance here, remember guys, I'm not looking at this end, I'm looking at this end. Okay? So your upwards force would be what? RA. Right? And with shearing force, the word force, do we take distance into account? No. When I tell you upwards force equals downwards forces and we're doing the test, do we do anything with distance? No. When I tell you moments, we use distance, right? So shearing force, bending moments. So when you're doing your calculations with bending moments, you'll have to use force times distance. With shearing force, you would just use force. Okay, so positive RA, that's the only upwards force there. Right? So this is how we're working our shearing force. Right? You need to take the algebraic sum of all the forces to the left or to the right of where, what's the rest of the word? Of the section being where it was fractured or bent, right? Okay. After that, now if we set up is positive, whichever forces act down on the left hand side is negative. Now we have two forces that act down, okay, which is W1 and W2. So to calculate the shearing force, it will be positive RA minus W1 minus W2. Do we all understand what I just said? Who's confused?
So which one is W1 and minus W2? Is this one?
So remember we're looking at the left. So from this diagram, we're looking at everything on the left.
Okay.
Upwards is positive. These forces acting down will be negative. W1 and W2 are acting down.
Okay.
Right. Now for the bending moment. Now with bending moments, I told you how you would normally work out a bending moment.
Force times time.
Force times time.
Times distance.
Force times distance. Okay. So same story like how you did this. Your upwards forces would be positive. Your downwards forces would be negative. So you would say RA multiplied by what? A. Because it's this distance of A away from the where it fractured, okay? Minus W1 times A1 minus
W2 times A2.
W2 times A2. And that will give you the bending moments to the left. Is that okay? Yeah. What? To the right. Okay, so your shearing force now, your QS will be equal to, now when we're looking at the right, which ones are positive, or when you, is up or down positive?
Down. That's positive.
Down is positive, so up would be negative. So whichever forces are acting down would be your positive force, whichever force is acting up would be your negative force. So we have one force that acts down, right? So this will be W3 minus RB. And that will give you your shearing force on your right hand side.
This one is tricky, yeah? Because if you once you confuse the two, say RB minus W3, then you're screwed.
But this is not the
It's not the logic.
they hardly test how they testing now. You'll see in the next example. I'll tell you how they mostly test. But I'm not saying don't know it. I'm saying I need to know it, right?
Yeah.
Okay, bending moment. It will be exactly like how this is, but with the addition of distances. Yeah? So this will be W3 times A3 minus RB times B. And that will give you the bending moment on your right hand side. So are we okay with that? Oh yeah.
So on this one, the right hand side will obviously be heavier. You have more.
Yeah, on your left hand side, it will be bending. Your bending moment will be higher than on the right hand side. Probably like depending. Also, it depends on how much weight is being added onto it. Like what happens if on the right hand side you have 1,000 newtons, but on this side altogether you only have like 25 newtons.
So it bends closer.
Yeah. Okay. So that's basically the theory they want to know. You all to know that, right? So far we all okay with that, yes?
Yes.
Good.
Can you take that down?
Yeah. Let me just pause it real quick.
Breaking point, you call it the shearing point.
No, just call it XX because, yeah, don't call it a specific shearing force or bend because you're using on bending moment as well. So how can you say shearing force in bending moment?
I'm trying to make some sort of a note to say that.
Section, just call it section. XX, call it the section. X dash X section.
Section, okay.
Okay, so now we're looking at your shearing force and bending moment diagram. Now this is the important thing I need to know, okay? So, the following rules or procedures should be followed when drawing a shearing force diagram and a bending moment diagram for a conventional system of graphical representation. So the first thing you would do is draw your loading diagram according to scale to represent the distribution of the loads. So, this is an example of a loading diagram which we always do when we're writing our questions. Now pretend that you finished solve for your reaction forces A and B. This is what you got, and now you need to draw your shearing force and your bending moment diagram. Next thing they tell you, draw the shearing force diagram directly below, okay, on the horizontal line. Start at the left hand end of the beam and move to the right. Although we don't draw the y-axis, the force is indicated blah blah blah. Right? So, shearing force. So you would draw a horizontal line directly below your loading diagram, and you're going to see why you should draw it directly below and why your stuff should be to scale. So how you would do this now? Please pay attention. Every time I leave it, you can come back to it later. Right? Pay attention. Right? What you would do, your upwards forces you add, your downwards forces you subtract. So your upwards force you take as a positive, downwards force you take as a negative. Okay? So at the start of your diagram, directly below this, okay, you have a positive force that acts on the beam, yes? Yes, of 24 kilonewtons. So you would say that this line would move up to 24 kilonewtons. And then for 2 meters, it stayed at 24 kilonewtons until this force of 10 kilonewtons. Yes? Okay? So you would say 24 minus 10, which would be 14. So it will move down to 14 kilonewtons. So it carried on for another 3 meters until it had 20 kilonewtons applied to it. Right? So you'll say 14 minus 20, which would be minus 6. Kilonewtons, right? That will continue for another 2 meters until the introduction of another force, a downwards acting force, right? So minus 6 minus 20 would be minus 26 kilonewtons. This would continue for another 3 meters until a positive force of 26 kilonewtons acted on it. So minus 26 plus 26 would take you to 0. And this here is basically your shearing force diagram. Is that difficult? No, is that fine? It's not difficult, right? Whatever is acting up, you add. Whatever is acting down, subtract. So all this here is basically your shearing force diagram. You okay with it? Yeah. Nothing like that here. I can't do anything or difficult about
Yeah,
that.
there's nothing.
So the main thing is you need to ensure that this diagram is drawn properly firstly. Right? You need, because you need to ensure your forces are all in the correct place and stuff. You need to ensure that when you're working out your reaction forces, that your reaction forces were calculated correctly. Because remember that it's not going to work out properly here. And because your system is in equilibrium, you'll start at 0, you should end at 0 because you basically balanced all your forces to your supports. Your forces acting down to your supports that's acting up. Okay? Right. Now, let's look at how you would work out your bending moments. So bending moments, there's a calculation to it. It's not as simple as how the shearing force diagram is. Right? Can I take out the step?
Yeah.
Okay, so for your bending moment diagram, so how you would do your calculation. So you see over here I labeled it, or it was labeled and given to us as A, B, C, D, E. Wherever a force acted, they gave you the point in A. Okay, so A is a point on the beam where your reaction force of AX. B is a point on beam where your 10 kilonewton force acts. Okay, so now you need to work out the moment. How would you work out bending moments? This is how you work it out, right? You will either take to the left or to the right of that point. Okay? I am telling you that you will always take to the left of a point. Okay? So when you take to the left of a point, you would consider all clockwise movements as positive and all anti-clockwise movements as negative. Please pay attention there. So when you're working it out, so you'll say bending moments. Clockwise moments is a positive, anti-clockwise would be, and you'll see why I'm telling you how to do this, right? Because what would happen is that all the forces, if you're only considering to the left of a point, all the forces that act upwards would be a positive force, all the forces that act downwards would be a negative force. Because if you look at it, right, if I'm considering point C, right, this is point C, everything to the left of it. For this portion to move in a clockwise direction, it needs to be pushed upwards. For this here to be moved in an anti-clockwise direction, it needs to be pushed downwards. So to keep the calculation consistent and not to confuse yourself, take to the left of every point. That will instantly mean that you take clockwise as positive, anti-clockwise as negative. Your upwards forces will become positive, your downwards forces will become negative. Now you need to work out the bending moment at each point. So I will start with the bending moment at A. What is to the left of A?
Nothing.
Nothing. So what will be the bending moment at A?
0.
0. Okay, so this will be 0 kilonewtons per meter. Bending moment at B. So, where B is, so far guys, we all okay, you understand what I'm saying?
Yeah.
So you see where you find?
Yeah.
Okay, looking at where B is, what is to the left of B?
It's only the 24 kilo.
It's only the 24 kilonewtons, right? And remember we said whatever causes the beam to move in a clockwise would be positive. And upwards, I told you upwards would be positive. So, with a bending moment, how do you work out a moment?
24 times distance.
Times the distance. How far away is that RA, the force that's acting, from B?
2 meters.
2 meters. So this would be equal to positive 24 times 2 meters, which would be 48 kilonewtons per meter. Right? So far we go to that. Bending moment at C. Now everything to the left of C. How many things are to the left of C? 2. you have one upwards force, which are RA, and the downwards force of the 10 kilonewtons. Yes? We said upwards would be positive, downwards would be negative. So if you start with the 24, how far away is that from C?
5.
5. It will be 2 plus 3. Right? Plus, now down we said is a negative force. So it will be negative 10 times. How far away is that 10 from the C? 3 meters. Okay? And this would be equal to 120 minus 30, 96. Yes? 90, right? Oh, okay, let me show you also how you could, okay, let me do this on the left and then I'll show you if you could have done it to the right. It will be the opposite things observed, okay? But I'll do it after. Now let's move on to bending moments of D. Okay? Where D is, how many forces act onto the left of it? 3. 1 up, 2 down. Okay? So, positive 24 because up is positive. How far away is that RA from D? 7. No?
Yeah.
7. Yeah, 7. Okay? Plus, your first downwards force, downwards the magnitude would be a what value? A negative value. So negative 10 multiplied by how far is that 10 from your point D? 5. Plus negative 20. And how far away is that from point D? 2. So this would be equal to
Wait. Why is it? Okay, C, sorry.
C is down, right?
50.
50 minus 40. 78.
78.
Yeah.
78 kilonewtons per meter. Now, one more point we got, which is the bending moment at E. So, bending moment at E, how many forces are to the left of E? 4, right? So, this will be 24. The distance of RA to B, 10, the full length of the beam, plus negative 10 because it's downwards forces after this, right? Negative 10, how far away is that from E?
8.
Plus negative 20, how far away is that from E?
5.
Plus negative 20, how far away is that from E? 3. This here would equal to 0 kilonewtons. When you work it out, you'll see that. There's 240 minus 80, 160, minus 100, which is 60, minus 60, which is 0. Okay? So, and obviously, at either ends, it would have to be 0 because you need the system to be in equilibrium based on how your shearing force also looks. Okay? So this is how you worked out the bending moment at each point and where each force acted on it. Do you understand the calculation part? See, these notes are made on the top here. Very important for you when you learn, when you're doing a question yourself after this. Right? If you had to consider bending moments and you consider to the right of points, this would swap. So your anti-clockwise will now become positive and your clockwise will now become negative. But don't do that. I'm trying to keep us consistent and it's easier when you all stick to one method, right? Consider to the left, clockwise moments will be positive. Instantly you would see that whatever pushes it up would be a positive value. So your upwards forces will become positive. Now that we worked out the bending moments of each point, they tell you that 0.5 on the top of page 76, the diagrams are actually graphs. The coordinates perpendicular to and measured from the baseline give the value of a particular load effect at that section of the beam. So, what you will do, directly below your shearing force diagram, right? You will draw another horizontal, which will also be a 0 line. And you would start, right, at point A. Okay? What's your bending moment? 0. So, that will be your point A. Right? Point B. What's your bending moment? 48. So let's say let's see the below. Let's say 48 is there. Right? At point C, what's your bending moment? 19, this is 0, 48. The next one is
90.
90. At point D, your bending moment is
78.
and lastly,
0.
so connect your points. Oops. So all this here is your bending moment. Now what does this mean? If you look at your diagram, remember how you were saying that at certain points, wherever you put it, some things will bend more than others because there's no supports under it and stuff, right? If you picture a shelf and you have supports on either ends, and if you put all your weight on the center of the shelf, it's going to bend in the center. So where would you expect your highest bending moment to be? At the center. If you look at this, your highest bending moment is found where? At the center of this beam. Right? And as you move towards your support, your bending moment starts to decrease. Why? Because obviously there's support for it. Okay? That's basically the two diagrams that you'll be using, that you'll be calculating, that you'll be working with. Okay? Do you understand what I did?
Yes.
Who's completely confused?
In terms of for E, do we really need to calculate it?
No, as long as your system is in equilibrium,
Yeah,
it's always going to come back to zero. Wherever that support is,
yeah.
wherever that support would be, it should bring you back to zero. No, like wherever your last point is, that would be zero. I don't want to say that and then you get one where you have a beam here, your support is here, but you have a force acting here. It's not gonna the cigarette. So wherever the last point is, it should come back to equilibrium. Okay. Yeah. Any questions on that? Are we okay? Are we all still alive? We well? We good? It's easy.
It's a lot to remember.
There's nothing. Okay. So if you look at page 76, it's important. Please highlight this. Right? You need to know how these diagrams need to look. Okay, so they tell you that if your loading diagram looks like the way they have it, right? So if you have a beam and if you have two supports on it and you have a load that acts onto it, your shearing force diagram should look something like what it is below. Okay, if you have a concentrated load, which is a point load, your shearing force should look like what it is below, and your bending moment will be straight lines. Okay, joining the points. If you have a uniformly distributed load, that's different the way you would draw it, because your shearing force now, when you draw the diagram, like say for example you had a uniformly distributed load starting from here and moving on to here. When you are joining the point from here to roughly about here, you will draw it at an angle. Do you understand what I'm saying? Okay, you won't draw it as a straight hard line because it's not a concentrated load. Remember that uniformly distributed load will distribute a force from point A all the way to point C. Right? So you need to show that it's obviously causing it. As it moves towards the center point here, that's where you get maximum bending. Where it cuts your zero axis, that will be the most likely point where it will break. Understand? And obviously it will be the most likely point where you get your maximum bending. Understand? I'm sure you understand what I'm saying. Yeah. Okay, understand, right? At a point where you get your maximum bending, where this beam is bending the most, after a certain point of bending, what's the only thing that can happen after?
Okay.
It's going to break. And shearing force diagrams show you what? Where a break or a fracture will occur. So the point at which it will cut this here would be your most likely value at which it will be maximum bending, or the point where it actually broke. Okay? You understand that? So the diagram is important. You'll see as we do more examples, when we do a uniformly distributed load, you'll see you'll have to draw your bending moment as a curve and not as a straight line. Okay? It's okay, but how are we doing our time?
25 to 2.
Let's do 1.5. Okay? Okay, so please make a note of that. Next page. We observe the following properties from the loading cases shown in figure 1.8. Let's figure 1.8. Oh yeah, the bending moment there. So they tell you that the magnitude of a concentrated load at a point is represented by a vertical line in the shearing force diagram. What does that mean? You see where you have a concentrated load that acts on your loading diagram. See at the top where you have 10 kilonewtons? When you're showing it on your shearing force diagram, it's represented as a vertical line. See how when we came from 24, we moved 2 meters. When the 10 kilonewtons was introduced, we went straight down. Okay? That's what they basically say. The shearing force diagram is a series of horizontal steps for any part of a span carrying concentrated loads only. For bending moment diagram, the bending moment at a point is given by a sloping straight line. So it'll either slope up or it'll slope down. Yeah, you're wondering I'm looking. I'm looking at the top page 77. Okay. At point 2, for any part of the span carrying a uniformly distributed load only. The shearing force diagram is a sloping straight line, and for the bending moment diagram, it is a parabolic curve. So when you come to your shearing force diagram, if this was here, and you're drawing your shearing force diagram, so your reaction obviously first here would move up, right? And when you come into somewhere here, I'm just saying for example, right? When you're doing the force, you will have to show it like that for shearing force. And then you would move on to wherever you went, right? For your bending moment diagram, if you are drawing it, it will move as a curve. As compared to how the concentrated load, we just has a vertical line for a shearing force and a sloping straight line for bending moment. Okay? The more you practice it, you'll see that. At points where the shearing force diagram passes through 0, the bending moment has a maximum positive or negative value. Put an asterisk or something over there, right? You need to remember that. The point 0 is also called your point of inflection. That's also important because in the question paper or in the exam, where they ask you to calculate the point of inflection in magnitude and distance, or show what is the value of inflection or point of inflection or something like that. You see where your diagram on your shearing force cuts the 0? There? Right? You will need to work out what the magnitude is when you cut 0. Okay, in this instance here, it would have been no, it actually wouldn't have been that. You would have to work it out, the distance at which you cut it. But you see, because it just so happened that it cut it where 20 kilonewtons is, it would be 5 meters. Right? So after 5 meters, that's where you get your point of inflection. Okay, because normally your point of inflection is where your graph starts to turn the other way, inflection, right? Okay. So you see how in your bending moments, it goes up until 90, and 90 is where your 20 kilonewton force acts, right? After that, it starts going down. That will be your point of inflection. And that happens when your graph cuts your shearing force at 0. Cool. Okay, that's some theory, right? Example 4.5. Draw the shearing force and bending moment diagram of the following simple beam. Just give me 2 minutes to draw this beam. You think so, huh? Yeah. You take a picture?
Take a picture. No, take a picture.
Should you go?
So I understand that.
Yeah, yaona ndipo isaka nje ona mali bafuna umusufaka lero kuzana nebhimu lelo elukuzana ebuyinqondo hafu
What's bad and nearly best crazy.
yabona angithi bale unqamlo wafa angithi yona angithi futhi ngithi bonile abantu face ukuphoko wase straight line le ukuzala le force le inqamu wafa ifanele ishintshe ibe slope ingabi straight line uyayifika isicofe khona concentrated.
Okay. Right, pay attention. Right. So, this is what they gave you. Okay? They asked you to draw the shearing force and the bending moment diagram of the following simple beam. Never gave you a mass, so you don't have to worry about your gravitational force, right? Okay. So, they want a shearing force and they want a bending moment diagram. Now, to actually do that two diagrams, what do you need to have?
Your RIs.
Your I and RE. You need to, okay, so firstly, to get that, you need to have the value of all the forces that acts on the object. Right? Because remember the definition of shearing force is the sum of all the forces that act on the object at a section. To the left or right of the object at a section. Right? So, we need to know whether it's regarded up or down, we need to know all the values. So, we need to solve for this. So, we'll solve for this like how we normally would solve for any reaction forces. We will take the moments, right? So, we'll say take.
Now it makes sense.
How we call
Everything's worked out.
right?
Yeah.
Oh. Yes.
How many marks this question?
Lot.
10?
Okay, so I'm gonna call this side A and that side B, right? Because that's where the points are, okay? At the ends. So take the moments about A, right? Clockwise moments equal to anti-clockwise moments. Cool. So if you're looking at this end, what would cause the other end to move in a clockwise direction? Your downwards forces, right? So you would say 20 kilonewtons times how many meters? 2 plus 10 kilonewtons times plus 30 times 8 equal to Rax at point A. So the only other upwards force would be Rb times what's the distance of the beam? 10. Right?
Question. For this part, the down forces, we don't have to convert them to force newtons.
No, if everything is consistently kilonewtons, it's fine. Okay? So, 40 plus 50, 90, 16, 24, 330, right? So it says 330 is equal to 10 Rb, which implies that Rb is equal to 33 kilonewtons. Right? Okay. Okay? Then we'll say, take the moments about E. So far we're okay, right? This is normally how we normally would answer questions. Okay? Take the moment.
Is it E or B?
E.
No, I'm saying the bottom. Okay.
Yeah.
Yeah.
No, I'm calling this reaction
Of
for
course.
B,
Okay.
right? Don't mix up this and that because that's how you had the problem with the simultaneous one. Okay? This here is the okay, but in this instance, it's where the point of where it acts, right?
Yeah.
But you can call this ends anything. Okay? Take the moments,
So we call it X and Y.
anything.
Throw that in.
About E. I should have wrote this there, so I could have drawn here. It's fine. Okay, so you carry on as normal clockwise moments is equal to anti-clockwise moments. So, if you're looking at E, what would cause the other end to move in a clockwise direction? Upwards force. Okay, so RA, how far is that from E? 10, RB acts at 10, okay? I mean acts at E. So if upwards forces cause a clockwise motion, downwards force will cause a anti-clockwise motion. So 20 kilonewtons is how far away from E?
8.
10 kilonewtons is how far away from E? 30 kilonewtons is how far? 2. Okay? So you end up with 10 RA is equal to 270. 270 RA is equal to 27 kilonewtons. Okay, now if you do your test quickly, right? Up must equal to down. Your upwards forces is 27 plus 33, which is 50. 20 plus 10, 60, sorry. I'm listening to you, stop listening to you. 20 plus 10 is 30, plus 30 is 60. So you know your upwards forces is equal to your downwards force. This here is cool, right? This is exactly how you will answer in the paper. You don't need to write that part down, you just need to know up must equal to down, carry on.
Oh, you don't have to write it. That's just where our
Unless they tell you,
Sure.
yeah, and test your answer.
okay.
Then you know what they must do, right? But they very rarely ask because there's so much other things they have to give you marks for that. So, we did this, right? Before we draw our diagrams, let's calculate the bending moments one time. So when we go, we just draw diagrams only, okay? So, let's say bending moments. So we take everything that's to the left of a point. And if we do that, your clockwise moments is equal to a positive value. Your anti-clockwise moment is equal to negative. So this will automatically make up as positive, down as negative. Cool? Nice. Let's take the bending moments at A. Bending moments at A will be equal to? What's to the left of A? See, it's gonna take a while to get used to. Right? No, you just not the forces like that, the points, all the forces that's to the left of it. There's nothing to the left of it, so it'll be 0. If you do it the other way, you know, like to the right hand side.
Yeah.
If you did it to the right hand side, okay, now I don't want to confuse you again. Okay, this would be 0 kilonewtons per meter. Bending moment at B. Bending moment at B. How many forces are to the left of B?
Only one.
Which force is that? RA is moving up or down? Which is a positive value. So this here would become, it would be 27, 27 kilonewtons, right? So this would be 20.